do we measure pressure? Well, it turns out it has something to do with why Mr. Bergman became a scientist. As a young boy, well, instead, let's have a look.
So you may not know this, but one reason I'm a science teacher is because I played in the bathtub as a child. And when I was playing in the bathtub, I had like a cup of water, and I discovered something that I thought was super cool. We're gonna look at that today. So I got a cup. This cup is filled. It's filled? It's empty. No, it's filled with air. So if I like have a seal, and I take this and I put this in this vat of water, watch very carefully as I push down. You'll notice that right down here, some water is trying to push itself up. It is, in fact, pushing itself up in here. But there's all this air. So let's see what happens if I let a little of the air out. Now notice if I like bring this up, that there's water. This is where it's kind of fascinating. There's water above the level of the water. Isn't that weird? What if I were to let some more air out? Like quite a bit more air. Now there's a lot of water above the waterline, but there's still the air trapped. And then if I let all of it out, look at this. Now we've got water above the level of the water. It's crazy. What's happening, here's the weird thing, is what's causing this is the air pressure is pushing down on the water, which is pushing the water up. So how high can you go? Well, let's try something a little taller. I've got a graduated cylinder, a tall graduated cylinder. I'll put this in here, right? I'm gonna fill it up, let all the air come out. As we say, burp it. If I can get that last bit of air out. What happens now is if I turn this upside down, the water level goes all the way to the top. This is crazy. Wait a second, so how tall, is there a limit? Can this go up like 10 feet, 5 feet, what? So if I was to like put water and go higher and higher and higher and higher, how high would it be? Turns out you have to go about 30 feet if you're at sea level. And above 30 feet, let's say that you have a 35-foot tube of water, 5 feet would be empty space. But that's not very convenient, is it? This is actually how we measure pressure. This is called a barometer. And we could make a water barometer, but we did a 35-foot water barometer. But there is a solution.
So what if you had a much, much denser, heavier, if you will, liquid? I'm standing at a mercury barometer here at the school. And if you look right here, mercury is this really cool, super liquidy stuff. And it's the same thing. It's the inverted water cup in the water. But since water or mercury has a density of like 16 or 12 or some big number, what happens when we flip it around here, take a look right here, is that the height of the mercury can be measured. And remember I talked about how 30-foot feet, there'd be nothing above? Right above this spot right through here, that's just empty space. So when you look right here, you can see that the pressure is at 750 right here. This is the pressure of the day. We're close to sea level here in Houston, and that makes a lot of sense. It's a little bit of a lower pressure day than normal. And we're about 750 because the space above here is just gas, empty gas right above here. And because it's like the thing, right? It's like the upside down water thing, except it's filled with mercury.
So as you can tell, you guys can recreate this dramatic moment in Mr. Bergman's childhood at home in your own sink, but there's some science going on behind that, and probably the best way to look at that is to
Let's draw a picture. We got a tub of water, right? And then we put the device filled with liquid. Now this could be water, right? But it's filled with water. But let's pretend it's like the mercury and it's filled with mercury, which is blue, which is true. But then what's up here, Mr. Dimitrowicz?
Well, it depends if you've reached the maximum height. Let's pretend you haven't reached the maximum height. And why is this water going up to begin with? So let's pretend the water goes to right here, right? In here, you're going to have some air particles that are creating pressure.
But then there's some other gas particles that are pushing down, which of course pushes this up.
So pretend you have this, a massive amount of particles, and here you have a few. Won't these gas particles want to go in here?
Yeah.
But there's water blocking the way and they can't go through this. So therefore they go up.
But if you completely burp it, and it isn't water, it's something short, some more dense liquid like the mercury we talked about a minute ago, it's going to go to a certain height, and then there's going to leave a gap at the top. You can't push it up an infinite height. Remember we said 32 feet for water and 760 millimeters neighborhood for mercury. So how do we measure pressure in light of that?
So the reality is we can take this barometer and we can go to different heights around the world. Now we talked about going specifically to Colorado, and the reality is there's less pressure, so there'd be less particles on the outside pushing down. So would the liquid go up quite as high, Mr. Bergman?
Not in Colorado, but let's say we're here in Houston, which is pretty close to sea level. What's the average pressure on like the average day?
760 millimeters high.
Now remember, that's actually measuring, here's a meter stick. If I were to measure this, it's literally how tall it is in millimeters. A meter stick is 1,000 millimeters, so 760 is this height right here, okay? So you just measure how tall, that's actually how you measure pressure?
Yeah,
How tall
it's
the
how
column of
tall-
mercury is?
Yeah, and we use we use mercury instead of water because who wants to go around with a tube that's the size of
32.
this room?
Yeah.
But the guy who did this, his name is Torricelli, and so boys and girls, if you ever want to be famous for something sciencey, we name it after you. So the guy who did this with millimeters of mercury, his name was Torricelli,
So we call that a TOR, T-O-R-R.
T-O-R-R, in honor of him. But again, this is kind of an awkward unit. Who wants to be talking about millimeters of mercury? So to standardize it, we came up with this idea that the pressure we feel at sea level, which is 760 millimeters pushing up mercury high, we're just going to call that 1 atmosphere.
So it's 1 atmosphere. So, and there's one other unit that we sometimes use, and that's called a kilopascal. And a kilopascal is, we're not going to use much of this. We're probably going to use just mostly atmospheres and torricellis. And yeah, so a kilopascal means 1,000 pascals, by the way. So you can also say 101,300 pascals. All right, so let's do a quick conversion. I think that's you. So when I was in Woodland Park, Colorado, what we found is that the average pressure was about 600 millimeters of mercury on an average day. So if we've got 600 millimeters of mercury, because there's less pressure there, higher altitude or whatever, then what is the number of atmospheres? So what would you do on that, Mr.?
Well, we always start with our train tracks because that's how we've learned to do everything, right?
600 millimeters of mercury over 1, right?
Over 1. And then here's where we're really going. This is the conversion we're going to use.
Yeah, yeah.
We're going to go from here to here.
So the millimeters of mercury goes in the bottom. I see that, and that's the 760 number. And then you just put 1 atmosphere on top. This is easy. It's just 600 divided by 760. Got my calculator out, and that comes out to 0.789 atmosphere. So about 80% or 78.9% of the air was where I was living. Interesting implications about that. When you're living at high altitude, there's 20% less air to breathe.
Yeah, and we see ramifications. If you're like a top tier athlete, there's something do something called altitude training, where they go up to these high mountain areas, or they recreate it here at sea level. And essentially, what they're doing is they are doing what?
Well, so what they do is when you live at altitude, or you can sort of fake living at altitude with a hyperbaric tent, is that your body produces more red blood cells. And it produces more red blood cells, and that means that because you need so amount of energy, you need that oxygen, more hemoglobin molecules, and so that if you train at high altitude, you have more red blood cells. But then if you go and perform, you compete at low altitude, and you still have some of those extra red blood cells, then you can produce more energy.
Yeah, I mean, that's kind of, how long does it take to do that approximately?
You've got to be up there about 2-3 weeks. It depends on, human bodies are different, and a lot of it depends on fitness levels and a lot of things.
I have seen it running around the track here that someone was wearing like a Darth Vader mask, and I think they're trying to simulate that same thing where they're starving themselves a little bit of the oxygen.
There's actually a rule typically in the endurance athlete world is what you'd like to do is you'd like to sleep at altitude but train at low altitude, because you can't push yourself as much at high altitude because you just don't have as much air to breathe. You can't really perform at the same level, the same speed if you're a runner or whatever. But yeah, altitude is a very interesting thing. And one of our football coach used to tell me, he says, my athletes, it takes them an extra week to recover from the same injury when I used to coach at low altitude. So because there's less oxygen, that creates less opportunity for the body to repair itself. So there's negative effects of it, but also positive effects for certain types of athletics.
And all of that we got from burping a container that you can do in your own home. Yeah.
Who would have thought?
We're going to do some really cool stuff in class the next couple of days, but anything you want to leave us with?
I'm just going to make sure we include the unit right there. You have a naked number there, Mr. Dimitrievich.
Just trying to make sure that you guys are catching things. Good job,
Yeah.
Mr.
So
Berman.
0.79. So we'll see you in class.
Indeed.